and you guys are the loyal band of merry people. Okay? I have no idea what that means. Don't try to play that album backwards because it won't sound like anything at all. Let's see. So today we're actually covering, what are we covering? I lost my little syllabus thing, of course. Today we're continuing with the EM algorithm. By the way, we also have a makeup lecture today at 5:30 in E129. So, okay. So, are there any questions? Okay, good. I'll go back then and look at the document camera. Okay, so we're actually a little bit ahead of schedule, I think. We're on 8.4. Oh, document camera. We're supposed to be on 8.4, the EM algorithm for Gaussian mixtures. So I think we kind of did this already. But everybody kind of goes through this. It's important to go through this once. So you calculate the Q function. So the key to calculating the Q function efficiently, I mean, you can just start plugging in here and grinding away, okay? But it would be pretty painful. What you really need to do is like put it in the right form. And I mean, there's other ways of doing this too, okay? But I've tried a lot of ways, and I guess to tell you the truth, my memory's not even good enough to remember all the ways it doesn't work, okay? But I've tried a lot of different ways, and this is one of the easier ones. Like, it only is a page calculation. But by expressing the log likelihood as this sum, okay? The reason you do that is that when you take the expectation, x is the random variable, you're going to be taking the expectation over. So when you have delta functions of random variables, then that's going to work out nicely because the expectation of this delta function is just going to be the probability that xn equals n. Because it's only 1 when those two things are equal, so the expected value of it being 1 is the probability of it being 1 times 1 plus 0 times the probability of it not being 1. So it's just the probability that it is 1, right? So that's why you write things in these strange forms that have these sums over these impulses, because when you take the expectations, it works out nicely. So this is then the joint log likelihood of y and x together. Okay, so we're assuming that the pairs of x and y are independent. So when you take the sum, that's equivalent to taking the product, and the product is what you would do if you take independent random variables distribution, right? So then you plug this into here and you get this double sum. So when you take it, then you can compute the Q function by taking the expectation of that, and you get this nice little form here. So it becomes like, I'm just trying to think how to think about this. So if you have this sum, so this is like the log likelihood of y and x together if you knew y and x, right? So if you replace n here by x at n, if you knew x at n, right? M is like the class associated with x at time n, right? No. Let me say that a little more slowly. Clear. So basically you have this thing which is x of n is equal to n, right? So n is the class associated with x at time n. So if you wrote this probability out, if you had the log of p of yn given mu of xn, right, and sigma of xn, plus the log of pi of xn. This would be like the log likelihood of the joint distribution of x and y, right, at time n. This is just the probability of yn and xn together. It's actually the log of that, right? These things are equal. This expression, let me get rid of that. This expression and this expression are the same, okay? Because this, okay. Does everybody see this? Because it's pretty straightforward. Part of it is just waking up on a Monday, okay? So, okay. So this is conditional probability of y given x, because y only depends on x through mu and sigma, the mean and variance, and this is the probability of x. So you take a log of them, and you get the sum of the logs. So this is equal to that. These are equal, right? Now, if I take this and I sum this from n equals 1 to n, right? And I sum this from n equals 1 to n, well, that whole thing is going to be equal to the log of the probability of y and x, right, together. So the joint distribution of y and x together is just this, okay? Now, if I were solving the maximum likelihood estimate and I had x and y, and I wanted to find the parameters, then what I would just do is maximize this thing, right? I take theta hat would be equal to the R max over theta of the log of p sub theta of y and x together. The problem is I don't have y and x, I only have y. So if I take this expression here, and I take the expectation over the various possible configurations of x, I get this. That's what it is. This expression right here is just the expected value of the log likelihood of the joint sequence where I've taken the expectation over x. Now, I can't just take the expectation of anything. I have to take the expectation of the log likelihood to form the Q function. Okay? But so in that form, this looks a little complicated because you say, well, I have all these sums and these variables and these indices, and I'm getting a headache. Okay? But you know what? When good chess players, of which I would not count myself, okay, when they play chess, they don't look at the individual pieces. See, when I play chess, I love to look at the individual pieces. I go, oh, look, that pawn's right in front of that rook, okay? And I go, oh, I think I'm going to take it, okay? And then I do that, and then my opponent, who's a much better chess player than me, takes all my pieces, okay? Immediately afterwards. Because I've only looked at the very local move, okay? But a good chess player looks at the whole position of the board as a unit, right? And a good signal processing, model-based signal processor looks at this expression as a unit. I don't actually look at each little character in it. I look at it as a big piece, okay? The sum over n is summing the terms in time. The sum over m is summing the terms over all the possible classes. And then this is an expectation, because I have a probability in there, it's a conditional expectation of x given y and theta prime, of the log likelihood, right? So that expression has meaning to me, and it's the Q function. Now what do you do with the Q function? The whole idea is you've got two thetas. You have the theta and you have the theta prime, okay? The theta prime is the old value of the parameter, and the theta is going to be the new value of the parameter. So I want to pick the new value of the parameters to be as large as possible given the old. Why? Because remember, when we go back, we have these various plots. Where are my various plots? Hold on. This is 160. Various plots. I know here I have a various plot over here somewhere. Here are my various plots. So here's the plot. And the lower bound is the Q function, and the upper bound is the true likelihood. it's not the best drawing in the world because I'm not a very good artist, okay? But the one lower bound to the other. So if I make the lower bound larger, the actual function has to be larger too, okay? So you're maximizing a lower bound, right? Okay, you maximize the lower bound. So when we maximize this lower bound, we've got to make the cost, the actual log likelihood bigger. So this is now, I just rearranged the terms. Oh, I actually plugged in the explicit form for, this is 162. Somehow or another, I lost that quickly. That was pretty amazing that I could lose something that fast. Come on. There's something about being under the pressure of, oh, here we go. Okay. So, now, this is, the Q function, right? I've actually plugged in now the actual distribution, oh, here it is. I've actually plugged in the actual conditional distribution associated with the Gaussian. So here I just wrote it as symbolic form to be clearer. And here I actually plugged in the explicit distribution of the log Gaussian, right? So this is the Q function. And now I'm going to maximize this. So now, and here's the explicit distribution for this conditional distribution of x given y. So just to make the notation a little simpler, I redefined it as f. So I didn't have to keep writing this messy thing here. And then when you write that down, then you have this. Okay, so f here is the conditional probability that the n samples from class M. So you sum that over all time, you get the total number of things, the expected total number of things in class M. And then here you get the fraction of them in class M. So this is the pi sum to 1. That's the maximum likelihood estimator. These are the maximum likelihood estimators of the mean and the variance. And the mean is just a weighted average of the y's, where the weights are the probability of ownership, and the variance is just a weighted average of the variance, right? Yeah, and these expressions, I mean, you don't just have to take my word for them. You actually can maximize this Q function with respect to beta is going to be mu, sigma, and pi. Because remember, theta here is a combination of mu and sigma n, or n, oh no, sigma n, yeah, squared, and pi n, for n equals 0 to n minus 1. That's what those are all the parameters of the model. One of the things that's important to keep track of in these mixture models is what the parameters are. These parameters, sigma has to be positive, mu can be any value, okay? The pi's have to sum to 1. So the number of actual degrees of freedom here, you might think would be 3m, but it's not. It's actually 3m minus 1. Okay? And this is what you get. So now if you're going to actually implement this algorithm, and the actual algorithm, you have two steps. First is the E step, where you calculate the probability of membership. So P sub nm is the probability that the nth sample is in the nth class. Okay? And that's this picture right here. So the first sample is in the m minus 1 class, or the 0 class. Okay? And then there is then you maximize, the M step is the maximization of the Q function with respect to theta. So the E step and the M step are a little bit, I mean, they're not terribly well defined in a sense. But generally, the concept of the E step is it's the expectation. So it's the actual calculation of the Q function itself. Sometimes there's no expectation to really compute, per se, because you just analytically write it down. Here there's nothing to compute. You know what it is. I mean, well, it's a little unclear what it means. I mean, so you might say the expectation is the calculation of these probabilities, of the membership probabilities, right? And then the M step is, once you have those membership probabilities, calculating the updates of the parameters. And then you repeat that. Every time you repeat it, the log likelihood will go up. And hopefully you'll converge to a local maximum of the log likelihood. Which brings us to convergence. So, in fact, we got a question about that. So I think a lot of this is review, but let me go over it, because we've already basically, the nice thing that, because I covered the surrogate functions and the method of majorization in the previous chapter, you've seen now this more than once. I'm a big believer that repetition is key to learning. Okay. So the fact that so I'm sorry if I'm repetitive, but I think it's important. But so you've seen this already once before. So it's the same basic idea. You're going to maximize this function. 66. Where's 67? Oh, shoot, I missed 67. I keep losing pages. 64. 63. 62. Okay, oh, here we go. 67. Oh, this is 68. What happened to 67? Oh, here's 67. So we have, I think this is all stuff that's a rehash. So basically, if you define this little h as being the difference between, as the VH minus VH at theta equals theta prime, then you just renormalize these things so that this little h function is 0 at your current parameter value. And then the renormalized q function with the lowercase q is actually a lower bound which is equal to the function at the current value. Then it just makes it a little more intuitive, and you can see that the log likelihood is the little q function plus the little h function. And now the little h function's derivative at theta equals theta prime has to be 0. Why? Because it's the global minimum at that point, so it's got to be a derivative of 0, right? The derivative being 0 at a minimum, at a local minimum, is a necessary but not sufficient condition. In other words, if it's a minimum, the derivative has to be 0, but if it's derivative of 0, it doesn't have to be a minimum. Right? So you know that it has to be, derivative has to be 0 because it is a minimum. And what that means that that the derivative of the log likelihood is equal to the derivative of the q function, right? At the current point, theta equals theta 0, the tangent. We've been over that. So therefore, the q function is going to lower bound. Okay, so it's clear that every step of the EM algorithm is going to make the log likelihood go up. But what isn't so clear is whether this is going to be convergent. Now, the sequence of log likelihood, so if you say Ln is equal to negative log of P of y, or I'll say this, hold on. Let me make this K. P of y given theta k, right? And if we know that the log likelihood is bounded above, So then we know, if we know that, for instance, LK is less than or equal to some L max, then we know that the limit, and we know that LK is greater than or equal to LK minus 1, then we know that the limit as K goes to infinity of LK has to equal some L star. Right? But we don't necessarily know that the limit as K goes to infinity of theta of K has to equal some theta star. Is that necessarily true? Well, the answer is not necessarily. So here would be an example. Let's say that you have a function which, let's say theta here is a vector theta 1 and theta 2, right? And let's say the cost function here is, see if theta is the norm of theta 2, 1, right? And let's say what happens is that you're on a circle, and you just keep going around the circle, right? So you go theta 1 equals sine of K omega, right? And theta 2 equals cosine K omega. Then you'll just keep going around the circle. And the cost function will reach a limit, but the theta won't. You'll just keep moving around. Now you say, well, okay, but those C's are not strictly decreasing. You can make them strictly decreasing by just having this spiral in, right, asymptotically. So, by the way, there's lots of ways for things to converge in problems. So, convergence in nonlinear systems, there's like, 8 different definitions of convergence. But in any case, it's not necessarily the case that the thetas will converge. But in most practical problems, they will. As long as, generally the intuition is this. If with each, if you can be sure that, let's say theta star is the minimum, okay, I'll call theta half to be the minimum, okay? And if each theta K has the property that, say, this norm K plus 1, if this is always less than some alpha times K, the previous one, where alpha here is less than 1, right, and say the magnitude of alpha is less than 1, then you're pretty much guaranteed, even if this alpha is small. The problem is that you don't want to stall. Even if this alpha is relatively large, like let's say it's 0.9, but as long as every time you get a little bit closer, then if you run enough iterations, eventually you'll converge. So there are a variety of proofs. And I give some citations. After a while, you just can, you get to be able to know, there are definitely versions of the EM algorithm you can come up with which will not be convergent, okay? But you get an intuition about when it's going to be convergent and it's not going to be convergent. If you have some kind of way in which you cause the algorithm to just stop getting closer, then that's going to be a problem. Like, for instance, I gave an example, if you use quantization, so if you don't have double precision floats, if you use integers with only 16-bit precision, that would cause you to stall because the quantization levels mean that you'll get stuck in a quantization level, and at some point you just won't move at all, okay? But as long as you sort of that's why I remember the example of if you have Jello down here, right, or silly putty, and you put a ball here, well, it'll take longer, but eventually we'll get to the ball bottom. If you put sand down here, so it's crunchy, then it'll just get stuck on a little piece of sand here. That's like the quantization level, and it'll stick, okay? But the general concept of convergence for these EM algorithms is like this. Okay, so first of all, there's a few proofs I give. This is 68, losing my notes. Hold on for a second. 65, 66, 68. Okay. So over here somewhere, two references. So I give a few references. You can look them up. I forget. There's a few classic references on convergence proof for this. And there's a number of others, but basically this is sort of the kind of proof, the way the proof looks. So I have a proof here. I think I have a proof for it. It's not a particularly interesting theorem because the conditions are so strong that it wouldn't apply in a lot of cases. But it basically gives you the idea, which is that if you have a sequence of parameter values generated by EM updates, and then we'll assume that the set that the parameters live in is an open set. That's usually not the case, right? So just a review, R, the real line, that's open, right? 0 to 1, that's the closed set, right? 0, 1 like that, that's open. Open, a set is open if you take any point in the set. So X, say, is a member of a set S, right? And then for all, okay, so the proof is that for all X a member S, there exists an epsilon greater than 0 such that the set of all, say, Y, a member of S, such that whatever your metric is, Y minus X squared is less than epsilon. This is called an epsilon ball. That's an epsilon ball. If there exists an epsilon ball such that the epsilon ball is a subset of that. So if that's open, if for any point there's an epsilon ball, it's part of the set. So the real line is open because if I take any point, I can take the interval plus or minus 1 around that point, and it's in the set. But this is not an open set because if I take the point 1, then any epsilon ball, no matter how small, is not contained in the set. But if I take the open interval from 0 to 1, if I take any point in the set, an epsilon ball around it will be contained in the set. Okay? So most of the time we're not minimizing these things on open sets. The problem is if you have a closed set, I kind of skipped over some of the stuff on optimization earlier. There's an appendix on convex optimization. But if you have a closed set, then what can happen is that the gradient is not 0 at the solution, at the minimum, because you fall on the boundary, and then the KKT, the Kuhn-Tucker constraints fall into play. In those cases, if you have a closed boundary, if you have a function, let's say, for instance, you have a positive set, this is from 0 to infinity. This is not closed, so not open. It's neither closed nor open, right? But in this case, if you have a function like this, its minimum, the gradient as the minimum is not 0 because it falls right on the boundary. So in order to exclude those cases that can cause confusion, I just did a simpler case here, assuming that omega is an open set, and that the functions h and q are continuously differentiable. Okay, that's not so bad. And that the limit exists. Okay? So let's say the limit does exist. Then in that case, you can show that at that limit, the gradient must be 0 there. Why? Because you can basically just exchange the limit and the function. So you know that the gradient of the q function okay, the gradient of the Q function at theta, so for any particular update step, the gradient of the Q function is going to be 0 at the updated parameter because that you picked the value that was minimum, or I'm sorry, maximum, so its gradient has to be 0 there, and it's an open set omega, so you can't be on the boundary of the space. So then, if I take the limit as k goes infinity, right, the limit as k goes infinity of 0, 0, so that has to also be 0, and then because it's a continuous function, I can take the limit inside of the function, and then I'm assuming both these things converge, so it's theta star, so that, and then Q at theta star has to be, the gradient at that point has to be 0, but the gradient of the Q function at theta star equals theta has to be the gradient of the log of it. So basically, you've proved then that if the thing does converge, it has to converge to a point in which the gradient is 0. And that means if it's a convex function, or if it's a strictly convex function or like a compact set, well then, if the gradient is 0, it must be equal to none. Okay? So that's sort of the nature of the proof. For real practical cases, the proofs get highly technical. Let's see. Okay, so now that's interesting, but, okay, so now the simplified methods, now this part here gets very interesting, it gets a little technical. So, the deal is this, we're going to come up with some clever ways of applying the EM algorithm, which don't require that we do a lot of complicated calculations. In order to do that, we need some heavy-duty tools, okay? So you're going to have to bear with me. So this section is called Simplified Methods for Deriving EM Updates. When you get good at this, you can basically just write the EM updates down out of your head, and you don't have to do any of the derivations. Okay? So you see all this stuff over here? You don't have to do any of this. Okay? Because, on page 163. Because you can basically just write the EM updates, they're intuitive. Okay? So you'd say, well, how could it be intuitive? Okay, well, we need a little bit of background. This is 163. Okay. Okay, so the exponential distributions and sufficient statistics. Okay, so why am I covering exponential distributions and sufficient statistics? Well, let me give you the answer, and then I'll, in words. So the way you can calculate the EM update is, let's say I have, okay, let me just do the EM updates out of my head for some simple case, okay? So let's say we have this. We have X. Let's draw that a little bit. Let's say we have here X1, okay? And then we have X2. And then we have Xn, right? And then for each X, we have Y1, Y2. By the way, this is probably a homework problem, okay, that I'm doing here. So now, let's say that Yn is distributed as Poisson with mean lambda Xn, okay? Now, we know that the distribution of a Poisson random variable, right? It's like, help me here, guys. So it's going to be lambda n, what is it, to the k? Yeah. To the k, right? Over k factorial times e to the minus lambda m, something like that? Is that correct?
Yep.
So that's the probability that yn equals k given lambda n is the rate, okay? Now, if I observe, now let's say I have let's say I know that they're all, let's say that x, so and xn here is either d with probability that xn equals m is equal to pi m, okay, it's equal to pi m, right? And and here n equals 2, just keep it simple, so there's two classes, okay? So now let's say that if let's say all the x's are equal to 0, so they're all 0. So in that case, the ML estimate of then lambda 0 hat, the ML estimate of the rate of the Poisson, you can do the calculation, but it's going to turn out that you just sum from n equals 1 to n, yn, and you divide by n. That's what a Poisson random variable is. It means lambda is the mean of a Poisson random variable, right? So I assume everybody has a basic understanding of Poisson random variables, okay? So if I know that they're all Poisson and they all have the same rate, then I just average them all, I sum them all together and divide by n, and that gives me the average rate, right? This is the maximum likely estimate of the random variable, okay? Now, if you do the EM update, it's going to turn out, I can write the EM update down. I don't even have to do a bunch of calculations. It's going to be this. It's going to be lambda hat m, right, is going to be equal to the sum from n equals 1 to n of yn times, now this is going to be the new value, times the probability that xn equals m given, of course, the value y, and lambda k, or I'll just say theta k minus 1. That includes lambda. So you compute for each entry the expected value is probability that it's in class m, and then you divide by n. And what's going to also happen is that pi m k hat is going to be 1 over n times the sum from n equals 1 to n of the probability of xn equals n given y and theta k minus 1. So people might say, well, how do you know that's true? Yeah.
Shouldn't that be like n? It shouldn't be.
Yes, this should be n.
Did you know?
Yes, thank goodness that someone's actually paying attention. So that actually should be n hat n, and then n hat n should actually be the sum from n equals 1 to n of p xn equals n given y and theta k minus 1. So you say, oh my gosh, well first of all, okay, I need to tell you something, which is that I think this is really cool, okay? And the second thing I need to tell you is, it may be that anybody who thinks this is really cool is deeply disturbed, okay? Okay? And perhaps you think it's really cool too, okay? But it seems like a lot of gobbledygook equations, but it means something very simple, right? Which is that basically you just pretend you know the class of each sample by using, in place of the class, you use the expected value of the class, and then you calculate the maximum likely estimate given that guess probability. Now, it's a circular reasoning because the theta here was your last guess of the parameters, which might have been wrong. So then after you do that, you have to repeat the process, and you keep doing it in hopes you converge. The answer is you will converge, because each time the likelihood is going up, right? It's not to converge. So So the beauty of this is that I never wrote down any Q equations or anything. I never computed the Q function. I never took any expectations. I never did anything. I just wrote it down, okay? And, well, it may in fact be that I wrote down the wrong thing. But I didn't. Well, actually I may have. In fact, I did. I just got corrected. But if it's wrong, it's mostly wrong because I just made a silly mistake, okay? It's basically correct. Why? Because I know something you don't. I know that the Poisson distribution is an exponential distribution, okay? So most distributions you're used to using, with the possible, there's only one distribution you may know about that isn't exponential, and that's the Cauchy distribution. And nobody ever uses the Cauchy distribution except in homework problems and exams to prove that there's something that isn't exponential. So it's just like exists as a counterexample, okay? Okay, because it has infinite expectations. So, but all the other distributions you use commonly every day are exponential. So, for exponential distributions, it turns out you can only solve EM algorithms by taking the maximum likelihood estimator and replacing in the formula for the maximum likelihood rate, you replace in the formula for the maximum likelihood estimator the expected values of the sufficient statistic. See, the Y here is a sufficient statistic. The sum of the Y's is a sufficient statistic for the maximum likelihood estimate of the mean. So I replace the sufficient statistic with this expectation. So basically, you just write down the maximum likelihood estimator, and you replace the maximum likelihood estimator with this expectation. And it always gives you the right answer. Okay? Now, you say, why? That's what I'm about to explain to you. So I have to explain this to you, because if I didn't explain where we were going, your eyes would glaze over, okay, and you start thinking about something else. Now, that may happen anyway, but at least this is going to hopefully enhance the probability that you'll listen to me. Okay, now, so we're going to learn about first exponential distributions of sufficient statistics, and then we're going to learn about what are we going to learn about? We're going to learn about natural, okay, and then we're going to learn about how you can do EM updates for exponential distributions. So we're going to go through this material that some seems unrelated, okay, but pay attention. Because once you understand how to do this, then it'll be much easier to do the EM updates. You won't have to bother with any of the Q function stuff, okay? You'll just know the Q function's there, but you won't ever have to calculate it. So now this is how it works. First of all, there's a thing called the sufficient statistic. So a sufficient, I talked about this before. First of all, a statistic is any function of a random variable. But a sufficient statistic has a particular property that if P of y theta is a family of distributions parameterized by theta, okay, and if you can write it in this form, then P of y is said to be a sufficient statistic. Why? Because I can actually, any reasonable estimate for the parameter theta only needs to be a function of t. So therefore, let's say, for example, a sufficient statistic for the mean of the set of Gaussian random variables is their sum. If I know the sum of the random variables, I don't actually need to keep each of the individual random variables. So if I have like a billion numbers and I wanted to calculate their mean, right? I don't actually have, and they're Gaussian, I don't have to keep the billion numbers. I can delete that file and just calculate the sum of the billion random variables and keep that one value. So a sufficient statistic is like a summary piece of information. Now, a sufficient statistic for y is y. Y is always a sufficient statistic for itself. So sufficient statistics doesn't mean it's minimal, okay? There's another concept of a complete sufficient statistic that we won't talk about in here. And a complete sufficient statistic is not just sufficient, it's the smallest, most compact sufficient statistic, okay? But don't worry about that. Most of the sufficient statistics we'll talk about here are complete, okay? But don't worry about it, okay? The point is this, it's a sufficient statistic. Now, if you're calculating in particular the maximum likelihood estimate, so this is under equation 8.26, then what we need to do is maximize the log likelihood with respect to theta. So if we plug in the equation for 8.26 in there, then if we take the log, we get this expression. It turns out now that the maximum likelihood estimator is calculated by maximizing a function, the log of g of t of y is theta. Okay, so it's only a function of the sufficient statistic. So whatever that function is some kind of function. We'll call it f. So if you tell me the sufficient statistic, I can tell you the maximum likelihood estimator. I take the sufficient statistic and I plug it into the function f, and it spits out the maximum likelihood estimator. Okay? Now what is that function? I don't know. It doesn't matter. It's just that it exists. It's there. It presumably can be calculated. It exists. And if you've done sufficient statistics, you apply that function to it, and you get the maximum likelihood. Okay? Good with that idea? Okay, now, here is a specific example. Okay? So, we imagine that we have some IID Gaussian random variables with mean, mu, and variance sigma. So they're scalar random variables. I can write out the joint distribution, okay, of these things, okay? And, in this form, you can see that if I define b as the sum of the random variables and f as the sum of the square of the random variables, then the distribution of y and theta is a function of these two quantities, okay? So in equation 8.29 and 8.3, one is b and the other is f, and those two scalar variables are sufficient statistics together for the maximum likelihood, for the estimate of theta, where theta is the parameter of the mean and the variance. And the particular form of that function is here. So I break it down, okay? So h of y in this case is 1. So there's this idea of h of y and g. In 8.2, there's two functions here that have to be specified, h and g. Right? So here h is 1, and g is the function which maps. This is a vector of sufficient statistics, and that's a vector of parameters. By the way, b and f, are they numbers or random variables? They're random variables, right? Because they're statistics. Statistics are always random variables because they're functions of random variables. Okay? Okay, now, okay, fine. That's good. Now, that's 178. Okay. Now, in addition, we're going to have this concept of a k-parameter exponential family. An exponential family has a specific form, which is that the distribution of y given theta is an exponential of the interproduct of a function of the parameter set with the sufficient statistic. Now, this is any function of the parameter set, so it could be a nonlinear function of the parameter set, but it's just the sufficient statistic. So what this means is that the log of the probability distribution of an exponential family is a linear function as a sufficient statistic. Okay? Plus a bunch of other gobbledygook. Okay? Now, so if that's the case, this is not just a sufficient statistic, but it's what's called a natural sufficient statistic, or a natural statistic for the exponential distribution. Almost every distribution you use is an exponential distribution. I mean, think about it. That's why, in fact, for things like the Bernoulli distribution, which aren't obviously in that form, we often rewrite them in that form. Okay? So we're going to go through that. So here is an example. So let's say for IID Gaussian distribution, it's a sufficient statistic. It's a natural sufficient statistic for the exponential distribution, because this looks like an inner product. See, here you have an inner product between f, b, and that's just 1, okay? That's just a constant. So here we have an inner product between the sufficient statistic and a nonlinear function of the parameters. That makes it an exponential distribution. So this is an exponential distribution. Read these notes carefully so that you get this in your head. Now what's going to happen is that, so here we go. Okay, here I show it. This is here's the multivariate case. In the multivariate case, it's the case, okay? So here we go. Okay, so you're going to go and study exponential distributions. You will use them, okay? And have great fun, and I'll see you this evening.